So good evening, everyone. Can you please confirm if I'm audible? Oh, yeah, thanks. So welcome to the live session for the course Digital Circuits. We are into the week 11 now. So the course is taught by Professor Shantanu Chattopadhyay. I'm Anant Singhal, a PhD student from IIT Jodhpur. So today I'll be assisting you in solving some of the similar assignment problems that have been given you in your week 11 assignments. So as you already know that like we are almost into the last part of this course, and couple of weeks that we have belongs to the microprocessor 8085, which is also a part of this course, which is actually a very old microprocessor, and like we'll be giving some or we'll be getting some very basic insights of this microprocessors based upon the question. So in the last week also we did cover some of the problems related to microprocessor, and yeah, we'll continue that maybe for today also. And as I already told in the last week that I'll be having the week 12 lecture on next Tuesday, that is I think 7th of October. That will be the week 12 session, and on 10th of October I'll be taking that final summary session that I'll try to cover up, or I'll try to tell you guys some of the important parts of this particular course. Yeah, so this is what I have planned out. So for today, as we have already covered, I'd say all the main components of this course are already covered. The microprocessor component is like a very small one, I would say. So again, I would say you should start revising your concepts. Like you might have already forgot about some of the combinational parts of the circuit that we covered till week 6, and then we went into this sequential circuits and all. So I would say please start revising, or please start to prepare for your final exams also. I think it is quite near now. So yeah, with that, I think we can start with the particular lecture. So let's start with the problem one. So again, there would be direct problems. I mean, some problems that might require solution, but yeah, most of the problems would be direct. So I hope that you all also I would encourage that you should also write your answers in the chat box. Yeah. So this is the first problem, that in Intel 8085 microprocessor, ALE signal is made high to. So maybe I'll give you a minute. If you know the answer, you can write in the chat box. Otherwise, I'll solve it. Okay, so again, this is a very direct problem. So in 8085 processor, we have a lot of different types of signal. You'll see some of the instructions that have been covered in your lectures in throughout the questions that we covered today. So ALE is another type of signal which is also called as the address latch enable. So in the last class, we already discussed about that we have in our 8085 processor, what do we have? We have a 16-bit microprocessor, right? Or sorry, not 16-bit, we have 16-bit address lines. We already covered this, that we have from A15 to A0, and out of those A15 to A0, A15 to A8 are in one bunch, and A7 to A0 are in the other bunch. So basically only 8 of these are used for the data bits, because it is a 8-bit microprocessor. So this is what we call as the higher order address bus, and this is what we call as the lower order address bus. So whenever you enable or whenever you make ALE to 1, so what happens exactly is, so let's say we make ALE is equals to 1. So as the name suggests, it enable the latch of the address level. So whenever you make it, it basically puts the data in the lower bits of register. So this becomes 87 to 80. So this is what we have already discussed in the previous class. So to do that, actually to put the data into the lower order address bus, we need to make this ALE equals to 1. while doing the coding. So the correct answer to this problem will be in 8085, ALE signal is made high to enable the data bus to be used as a lower order address bus. So option D is the correct answer. I hope it is clear. I mean, some of the questions are very straightforward, so I'll just try to explain in very basic and we'll move ahead. So this is the next problem. So it says the clock speed of 8085 is. So this is also we kind of covered in the last class, but this is some precise question that has been asked. So
Answer D.
yeah, so the correct answer to this problem is answer D. So we know that in microprocessor, what do we have is we have a box and we have like two different frequency clocks that are of 6.25 megahertz exactly, and they are divided into two. So we can operate in between 3.125 to 6 point, sorry, 6 point, yeah, it's 6.25 to 6.25 megahertz. So any option would be the answer, but yeah, it's very precise, the option that has been given. So option D is the correct answer according to that. Okay, so I think we can move ahead. Okay, now it is asking about the CMA instruction. So if you guys already know, please type your answers in the chat box. Maybe I'll give you 1 minute and then I'll try to explain. Okay, so the CMA instruction, it stands for nothing but complementary. So CM is complementary and A here means accumulator. So it basically, whenever you do a CMA instruction, what it does, it performs the ones complement of whatever is there in the accumulator. So this is a very pretty direct question. So whenever you do a CMA, it basically do the ones complement of whatever there is the content in the accumulator. So I might have already told in the last class that we have several, like we have several registers, we have a accumulator, then we have memory components. So whatever is there in the accumulator, if you want to do a ones complement of that, you need to do the CMA. So CMA is like a keyword. So there will be some keywords that you will be seeing in the further questions such as LDI, then we have move, then we have a lot of instructions. So I'll try to cover some of those also in this particular lecture. So for CMA, it basically do the ones complement of the accumulator contents. Let's move ahead. Okay. So this is some kind of a solving question. So it says if the content of the accumulator register in 8085 is 4EH, after an arithmetic operation, what will be the status of the parity flag? So maybe yeah, you can try this out. You can take 2 minutes and let me know the answer. Then I'll also solve it. This is actually a pretty easy question. If you have gone through the lectures, this is very easy. Yes. Is there any doubt? Someone has raised their hand. Okay. Okay, so we have, as I said, we have accumulator in our 8085 microprocessor. So it says it contains 4EH. So first of all, this H here represents, so you will always see a H written at the end of every memory or the value of the component that is written. So this H basically represent that it works on a hexadecimal number system. So basically what do we have is, actually we have 4E in the accumulator. And by 4E you already be knowing, so it is a 8-bit microprocessor. So 4 is 0, 0, oh not 0, 0. So it is 0, 1, 0, 0 is 4, and E you already remember that we have A, B, C, D, E, F, which is 10, 11, 12, 13, 14, 15. So E is 14, which is 1, 1, 1, 0, I think. Yeah. So basically 8085 has a parity flag, which is a even parity generator, or a even parity flag you can say, not a generator. So by this I mean parity flag will be 1 when number of ones in accumulator is equals to even. So whenever we have a even numbers of 1 in the accumulator, your parity flag will get 1. That means your parity flag will get set. Otherwise, your parity flag will get reset. And whenever your accumulator is, let's say, empty, or we don't have any component, so it could be a don't care or a high impedance state based upon that. But yeah, in this question, we do have a component, so the answer could be either set or reset. So I think I've already told you the answers in some way. So as we know that in our accumulator currently we have 4E. So 4E has 1, 2, 3, 4. That means it has 4 ones. So what will be the value of the parity flag? Anyone? I mean, this is quite straightforward now. I hope I'm audible, right? Can someone confirm if I'm audible? Hello? Okay, yeah. So basically what do we have? We have 4 ones, that means we have even ones. So the parity flag will be 1, that is, it will get set. So option A is the correct answer to this problem. Okay, let's move ahead. Okay, this is a very good question. If you already know the concepts of microprocessor, so this is actually a good question. You can try this out. So it says in a 8085 processor, what do we have? We have accumulator content is this. So accumulator has 0 FH. Then the carry flag contains 0. So it says what will be the content of the accumulator after these instructions. So we have two instructions that are given. One is a RAR and one is a RRC. So both of them operate in a some certain way. So if you already know the operation, please let me know the answers in the chat box. You can take at least 2 minutes to solve this because this is actually a good question. So you can try it out on your own first. Okay. Is anyone aware of RAR and RRC, what it stands for? Okay, so let me try to give the idea then. So as I said, we have two types of rotations that happens in accumulator. One is RAR, one is RRC. So RAR is nothing but rotate accumulator to right, whereas this RRC stand for rotate again accumulator right. But here the change is it should be through the carry flag. So the C here stands for carry. So let me try to explain the operation, how exactly it happens. Sorry. Yeah. So RAR and maybe let's say RRC, I'll write here. So as we already know that we have 8-bit data, let's say from A7 to something called as A naught, and we have a carry flag which is, let's say, C naught. Similarly, so if I try to compare here also, so we have A7, so let's say A naught, and then again we have a carry which is C naught. So in RAR operation, what happens is there is just direct rotation of the accumulator to the right. So whatever is there in A naught gets rotated here, and whatever is the content is C naught, let's say this is C naught, is gets here. So basically this is the right rotation. So what I'm trying to say is, let's say we do the operation. So after operation, A naught comes in the carry flag, whereas the C naught comes here, the A7 comes here, and at last we have A1. So let's say A1 was here. So this is a direct rotation of the right bit. Then in RRC, what happens? So if I say, so what happens? This A naught moves to the carry flag, and also this A naught moves to the last bit. So basically your carry bit is getting lost. So what I'm trying to say, after this operation, let's say we do it, so the carry flag will contain A naught, and the accumulator will contain A naught, then A7, and then A1. I hope the operation is clear. Please, can you please confirm if it is clear to everyone? Okay. I'm assuming there are no doubts. So now you already know how the exactly this RAR and RRC works. So for RAR, or sorry, the accumulator has 0 FH as its content, and the carry flag is 0. So can you try to solve this problem now? Please let me know, otherwise I'll solve by myself. Okay, so let me do that then. So initially we have 0 FH. So let me write, so 0 and F are the actual contents. So 0 means the 4 bits are 0, and then F means 1, 1, 1, 1. So this is initial. So both of them has this. So now what is happening? RAR is happening, and the carry flag is 0 as the question says. So I'll write 0. So as I said, the operation is like this for RAR. So what will happen? Yeah, so what will happen here is, so basically this 0 will move here. So all of them will get right shifted like this. Okay, maybe have 1, 2, 3, 6. Yeah, so we'll have 0, 0, 0, 0, 1, 1, 1, and the carry flag will come out here because this is how our AR operation works. And then for a RAR, sorry, not RAR but RRC, the opposite of this happens. That means, let's say we have a carry flag. So carry bit will get lost. This A naught will come to both here and in the carry flag. So carry flag will be 1. So this will be, sorry, 0, 0, 0, 0, 1, 1, 1. So now this is nothing but this is 0 and this is 0, 1, 1, which is 7. And here it is 1, 0, 0, which is 8, and 0, 1, 1, 1, which is 7. So after RAR, what will happen? We'll have 0, 7H in the accumulator, and after RRC, what will happen? We'll have 8, 7H in the accumulator. So RAR is 0, 7, RRC is 8, 7. Yeah, so option C is the correct answer to this problem. Is it clear to everyone? Okay, I'm hoping it is clear. So let's move ahead then. Yeah. So the next problem says, how is the data accessed in a 8085 stack memory? So if anyone have any idea, you can write your answer in the chat box. I'll only give 1 or 2 minutes to this because this is again a direct problem.
Answer D.
Okay, so I've got an answer which is D. So okay. So again, let me try to explain this in a very easy language. So it says it has a 8085 stack memory. So stack is nothing but it store or return the address of a subroutine. So basically what happens or how it works in 8085, let's say we have a memory or any operation is happening and there are several subroutines that we have written in a code. Let's say we have the first routine which is named as S1, the second is named as S2. So let's say we start to execute a code. So what happens is, let's say our code is executed till here and we are at address, let's say X1 maybe. And then we have an interrupt and then we went to yeah. And then we went to S1 where again we start to operate and we have reached address line which is, let's say, till here. So then again we went to S2, let's say this get or this get executed and then we'll again come to X2 back. This will get executed again and then we'll come to X1 back. So what I'm trying to say, how it stores in the stack is, so let's say this is a stack. So we start with the memory. So let's say we got an interrupt here. So first of all, the stack will store X1 that I have to come back here so that I could complete this particular process. So again we do go to S1, then it is executing, then again it got interrupted. So again then it will store X2 so that it will remember that it has to come back here. And then we went to S2. So let's say it gets completed here, then we'll execute the X2 first, right? So we'll execute this first and then we'll execute this. So can I say that this is nothing but last out or last in, first out? So basically whatever that has been happened or whatever that has entered in the stack in the last has to get out of the stack first. So this is nothing but last in. So we have, like, at the last we have x2, we have entered the x2 in the stack and it has gone out first. So that is why we call it last in first out. So the correct answer or the correct procedure that the 8085 stack memory follows is LIFO, which is last in first out. So option A is the correct answer. So again, this might have been taught in the theory lectures, maybe in a lot of details, but yeah, this is a basic operation that I could explain in very easier words. So yeah, I think we can move ahead. So the next problem says how many T states are required to execute the following instruction. So maybe again take a minute or two if you already know how to the answer. So please write in the chat box. Otherwise, I'll try to explain this again. Anyone? Okay, let me try to explain. So this is again a very common instruction that we use. So it is nothing but, so LXI means load the data immediately. So I means here immediately, and X is a memory location that we have. So you see it's 1, 2, 3, 4. That means this is total 16 bit. So this is basically the command says load 16 bit in the register. I'm writing register as RP. So basically D means, so whenever there is a 16-bit memory, so there is always a memory or a register pair. Since every register is 8 bit, so D means we have a DE register pair. So we have only two register pair that can be used. One is BC and one is DE in the 8085 microprocessor. So 1, 2, 3, 4. So basically this is what it means. So we need to load 1, 2, 3, 4 in the DE register pair immediately. So if I try to say, it says how many T states. T states means what is the total time cycles. So LXI is 1, then D, then 1, 2, 3, 4, and then we have H. So first of all, this is load the D. So first of all, as I already told in the last class, that we first fetch the data. So in fetching, we require 4 T states. Then we have 8 bits of memory each. So for every memory, we require 3 T states, that is 3 time cycles. So the total states that we require, or the total T states, is nothing but 4T for fetching, then 3T, and 3T for reading or writing the memory. So the total states that will be required to operate this particular line is nothing but 10 T states. Sorry. So the correct answer to this problem would be option D. Okay, I think we can move ahead. So it says which of the following is an 8-bit register in 8085? I hope you at least know this, so please type your answers in the chat box. Okay, so we have different options. So the first is itself saying BC, that means this is 16-bit register pair. Then the stack pointer, we have just addressed that it stores the total address, the example that we see x1, x2 or something like that. So this is again a 16-bit. Then the program counter also is a 16-bit register, and we have seen in a lot of problems now that the accumulator only states, or sorry, not states, but store only 8 bits. So the correct answer to this problem is option D. Okay, based upon that, next problem is also similar. So it says which of the following register is non-programmable. So please try to tell your answers in the chat box quickly. I'll wait for 1 minute. Okay, so again, this is a direct problem. So non-programmable means that cannot be changed. So accumulator, we have just seen that we can change the bits by using some of the operations. So B is again a BC register pair. So that stores or that we can change by doing H is again a HL register pair. That is a memory location. So IR is the one which is actually the instruction register. So this is not programmable. We just use it to store the instructions. So basically the correct answer to this problem is option D itself. Let's move ahead. So it says which of the following register pairs hold the memory location address for the instruction. So we have given an instruction to the accumulator which is MOV M, B, which basically says that we need to move the component or whatever is there in B to the memory location M. So yeah, I mean this is the hint that I can give you. So please try to let me know what is the answer. I'm hoping that you already have seen the video lectures for this particular week, because if you have already seen, then these questions are very easy. I mean, they can be done like in a second or something like that. So I'll try to give you a minute or two. Please let me know your answers in the chat box. Okay, so let me try to explain what exactly this instruction means. So it says, as I said, that move the contents of B to the memory location M. So let me write. So it basically move the contents of B to M, which is a memory location. So if you've seen the lectures, this memory location is nothing but a HL register pair. So let me try to give you an example. Let's say the contents or the B contains, let's say 1, 2H, for example. So what this instruction do is it moves the content of the B to our memory location M, which is nothing but HL. So let's say we have a memory, and at some memory we have this, uh, yeah, let's say we have this HL, which is some memory location which I can call, maybe let's say it is 8132H, for example. So it will move the contents of B to this particular memory location, which is let's say 12H. So for example, HL, I have taken example as 8132. So what this particular expression will do, it will move the content of B, which was 12H, to the memory location H, oh sorry, memory location M, and this M memory location is always stored in HL register pair, and the HL register pair, let's say for example it is 8132H, so it will go to this particular address and it will store the value of B here. So now it says which of the following register pair hold the memory location address. So register pair is HL. So the correct answer is option B. I hope it is clear to everyone. Okay, so let's move ahead. So this is now some instruction problem. So it says how many times ORAB instruction will be executed in the following program. So this is a program that has been given and it is asking that how many times this ORAB will be executed. So maybe you can try it out for 2 minutes and let me know what do you think the answer could be, and then I'll also try to solve it. After that, I'll try to explain each of these instructions and let you know the answer also. So till then, you can type your answers in the chat box. Okay, so let me try to explain that if you don't have any answer till now. So I think we have already discussed at least this instruction in one of the previous question. It says LXI, which I already told you, it means load immediately, right? So it says load the register B. So B is nothing but BC register pair, right? So since we have 16 bits, so it will immediately store 0010 in BC. So now we have a loop. So it will end when we have this condition. So we'll see what this is. So the loop starts with a condition which is DCXB. So DCX is nothing but decrement the bit. So what this line will do, so let's say this line has loaded this. Now it will decrement one bit. So it will come from 10 to 0F, right? So let's say this is 10. So if I do 10 and decrement of one bit, so it will be 0F. I hope you are able to understand this in hexadecimal. So now what we'll do, it says now move the content of C to A. That is move the content of C to A. So this is BC. So C has 0F, right? So the A will also have 0F. Now it says ORAB. So ORA is nothing but OR operation. That OR gate that we have, OR operation. So we'll do the ORA of B. That means, so we have accumulator in which the content is 0F, B, B has 0, 0. So we'll do the OR. So this will be nothing but 0F again. So this line for the first time will give you, okay, so this line will give you actually 0FH only because the OR operation is again same. So now the loop says J and Z. So J and Z, if you already know, this is nothing but jump not 0. So basically this means whenever your 0 flag is equals not equals to 0, this loop will continue till then. Once your jump not 0 flag, or let's say I'll write directly, whenever your 0 flag will become equals to 1, then this loop will terminate. So basically it will terminate when all the contents will become 0, 0, 0, 0 basically. Are you able to understand this? Okay, so let me try it. So the first loop has already ended and it has given 0 as output. So since it is not 0 yet, so it will run again and it will decrement one more bit, right? So the second time we'll have a 0E, then we'll do the OR of A to C, then it will again be 0E, then the next time we'll have 0 D, then so on. And at some time it will become 0, 0, right? Then the loop will terminate. So now the question says how many times this OR operation will happen in the following program. So it has started with 0F and it will end at 0, 0. So what do you think will be the answer? Anyone? I hope it is clear that we have moved from F to E to D to 0. So we have total 16 times to make it 0, right? Because 0 to F is nothing but 16 values. So the correct answer to this problem would be option C. Please let me know if it is clear to everyone how we have done that. Is it clear? At least respond yes or no. Okay, let's move ahead then. So we have again a problem. So it says what is the total delay produced by the group of instruction and the clock frequency is given. So again you need to just find the number of t states in every instruction and just multiply it by the frequency. That will basically give you the time. Okay, so for time we need to divide it because 1 by f is time. So maybe try this question out, take 2 minutes and let me know the answer. Okay, so we have MVI instruction, so we'll need to fetch the C. So this is 4T. Then every 8-bit memory contains 3T states. So the first line will be 4T plus 3T. Then we have an instruction which is again fetch. It will decrement it. So this is again 4T. And then, oh, so there is a loop. So FFH till this loop will become 0, 0. That till then it will basically run. So FF is already, we know that this is 1, 1, 1, 1, 1, 1, 1, 1, which is I think 0, 1, 2, 3, 4, 5, 6, 7. 2 raised to 7. Okay, so I think this will execute 255 times to make all of it to be 0 because it will start 1 by 1 to make this increment as 1 less and then less and less. So it will do it 255 times according to the number of bits. So again, the jump instruction itself has, let's say, so it will, first of all, it will fetch, that is 4T states, and every memory it will fetch. So it will be 3T plus 3T. And this is actually 255 times. I hope this is clear. So the total time I would say is 1 by f, as I said. So the T cycles would be, the first line is 70. The second line is, the loop will be, I mean, 255 times 14. So why 14? Because it's 4T plus 3T plus 3T plus 4T. So I directly written 14. And then if you remember, the last time that we'll be operating this, it will not run, right? Once it becomes 0, 0, 0, 0, 0, 0, 0, 0, so it will not fetch the last memory. So I'm like separating that -3 bits from this. And that frequency is 2 raised to power 6, which is given in the problem. So this will be your answer. Let me calculate this. So this is 255 times 14. Okay, which is something 1790 minus 3. Okay, so I'm getting something 1787 microsecond, which is 1.787 milliseconds. Okay, so the closest answer is option A. So yeah, it will take a total delay of 1.78 milliseconds to operate this particular loop. Okay, let's move ahead. It says what is the minimum number of T states required to a simple move instruction? What is this? Yes, so I do always provide these PDFs just after the lecture in the NPTEL link, which is provided by NPTEL team to you. And this video will be uploaded on the YouTube channel just after the class. So yeah, what would be the answer to this? Can anyone tell? So to have a move instruction, we at least need to fetch, right? So the minimum states for a fetching is 40. So hence the answer would be option B. So let's move ahead. So it says in the timing diagram, the read write, sorry, not the read write, but the write signal is typically active during which phase of, okay, so I think this is direct. So it is, I think, T1. Let's move this question ahead. So it says which addressing mode is used in the instruction LDA 4321. So anyone having any idea, you can try it out in the chat box and write your answers in the chat box. I'll give you 2 minutes again. Okay, so I've got one answer, I think, which is B. Okay, so let me try to explain all these options, maybe by giving some examples. So one is the question itself, which is let's say 4321H. I'll take few more examples. Let's say LDAM. The next I'll take is LDI, maybe 24H, and it asks let's say CMA. So in each of this operation, what is happening? So in this line, what is happening is LDA means the load the accumulator, right? So accumulator will get directly loaded to this 4321 value, right? So this is a direct addressing mode. And let's say if I would have written LDA to some memory location M. So as I have already told in this, so M is actually a HL register pair, right? So let's say the content would be something 12H. I have already given example, and HL has some value of 1123H. So what will happen? It will first go to that particular location, which is 1123H, and this accumulator content will be loaded. So this 12H will be loaded in the accumulator. So this is particularly the second one is, let me write it here, is a indirect operation or indirect addressing mode. Then the third option says it is LDI. So as I already told you, it is immediate. So immediately load the accumulator with 24H. So this is immediate addressing. And last is a CMA. CMA means we just need to complement the accumulator. We are not loading or doing anything. So this is a implied addressing mode, that we are implied to do the complementary of the accumulator. I hope all these operations are clear. So as a question says, we need to load the accumulator directly using 4321. So the correct answer to this problem would be option C. So these are the four addressing mode that we in general use. One is a direct mode in which we directly write whatever the address or whatever the bits we need to load. The second one is indirect, in which we do some or we do write some memory location. We fetch that memory location, and that whatever the data in that memory location is getting loaded in the accumulator. The third one is immediate mode, which is LDI. So whatever is written adjacent to this I will be immediately written in the accumulator, and CMA is the implied addressing mode. So the correct answer to this problem is option C. Let's move ahead. So it says how many flags are there in a 8085 processor?
Five.
Sorry,
Five.
did anyone say something? I'm getting some voice.
Oh, seven, sir. Five used and two unused.
Okay, so in actual, the total flag that we have are five only. So let me try to explain that. So we have 8 bits. I hope you are already aware of that. So it's D7, D6, D5, D4, D3, D2, D1, D0. So D7 has a sign flag, D6 has a zero flag, D5 is nothing, D4 has accumulate auxiliary carry flag, D3 is nothing, D2 has a parity flag, D1 is nothing, and D0 has a carry flag. So if I try to explain each of these flags, so S is nothing but the sign flag. So if the bit is negative, it becomes 1. If the bit is positive, it becomes 0. Z is nothing but the 0 flag. So let's say if your accumulator is 0, then your 0 flag will become 1. Sorry. Then we have auxiliary carry. So by auxiliary carry, I mean whenever, let's say we are doing a 4 by 4 bit addition operation. Let's say I'm dividing it something like this. So whenever there is a carry between the last bit, that is, let's say this particular bit to this particular bit. So let's say if we are having a carry from here to here, so your auxiliary carry, then AC will become 1. Then we have a parity. Parity I already told you, if we have even number of ones, then your parity is 1. Otherwise, if you have odd ones, then your parity is 0. And at last we have a carry flag. Carry flag means whenever at last we have the carry. So maybe, so if we have the last two bits and we are getting a carry out of those, then my carry flag will become 1. So these are all the actual flags that we have in a 8085 processor. One is a sign, the second is a zero flag, the third is auxiliary carry, the fourth is parity, and the fifth is carry flag. So the correct answer to this problem is option B. Let's move ahead. So it says the clock frequency of a 8085 processor is this much. The time required to execute every instruction is this much. The number of T states needed. This is actually very easy. We have done a similar question in which we found the T states and then we found out the total time. So here the time is given and the frequency is given. So you just need to find the T states. Maybe try to take 2 minutes and write your answers in the chat box. This is actually very easy.
Option D. Eight.
Yeah, so we have, as I told you, the T states times 1 by frequency was the actual total time that we are getting. So the T states will be nothing but the total time that we are getting into the frequency of the signal. So time is already given as 1.6 microseconds and the frequency is 5 megahertz. So this mega and micro will get cancelled. So 1.6 times 5 is 8. So we have 8 T states, which is option D. Okay, let's move ahead. So it says which of the following is not a valid 8085 instruction. Take again 2-3 minutes and let me know the answer in the chat box.
Option C.
Okay, so I've got one answer as C, so I'll maybe wait for 1 more minute and then I'll try to solve it. Okay, so we have already seen that we only have two register pairs that are accessible, which is BC and DE register pairs, right? So it says which of the following is not a valid 8085 memory. So first of all, LDAX means load the accumulator and X means extended accumulator. That means all the 16 bits needs to be loaded in the extension. So basically, if I can write in general, so it will be LDAX. You need to write any register pair here so that it works. So it basically copies the 8-bit content of address lines which is stored in the register pair RP to the accumulator. So this needs to be a register pair. Okay. This needs to, sorry. This needs to be a register pair. So whenever you write a B, this is obviously BC register pair. Whenever you write a B, this is obviously a register pair DE. But whenever you write a H, so for a HL register pair, as I already told you, we have a memory location which is given by a memory word M. So option D cannot be executed. So option B is the correct answer first of all to this problem. And INRM means just increment the memory. So yeah, this can be executed. So this is fine. So the correct answer would be option B, since we already only have BC and DE available register pairs. I hope this makes sense and clear to everyone. So let's move to the next problem. So it says what is the accumulator content after the execution of the following instructions? So this is a good question actually. Good question actually. So maybe try it out, take 2-3 minutes and let me know the answers in the chat box. Okay, just one hint. We have already seen RAR, RRC. So there is one more thing which is RLC, which is rotate accumulator to left. Yeah, and it is obviously through carry only. So yeah, but carry is not mentioned, so you just need to do the left operation and try to do the answer. Yeah. So again, take 2-3 minutes and let me know the answers in the chat box. Okay, so let me try to solve it if you don't have the answer already. So the first instruction says MVI, that means move immediately. So basically we need to move this 5 in the accumulator immediately. That means accumulator is 8 bits. So 5 means 0 1 0 1, then 0 1 0 1 H. So now we need to do the 3 times of RLC. So what will happen? It will rotate to left, right? So it will, sorry, it will rotate to left like this. So the first RLC, what it will do is it will rotate the bits. So by left we means so 1 0 1 0 1 0 1 0 3 4 1 2 3. Yeah. So the first line has done this. The second line has done this. The third line will move again, do the same thing. So it will be like the left rotation. So this one will come here 0 1 0 1 0 1 0. And it will happen one more time. 6 7. So again it will happen something like this. So so again it will be, sorry, yeah, so again it will be 1 0 1 0 1 0 1 0 H. So yeah, this is the final content, which is actually 1 0 1 0 and 1 0 1 0 H. So 1 0 1 0 is nothing but 10, which is A, right? So the correct answer is AAH will be loaded in the accumulator, which is option B. Okay, so please quickly try out this. Let's say we had, instead of 5 5H, let's say we had a accumulator which is 3 4H, and the same operation is happening. Please quickly let me know the answers in the chat box. Take 2 minutes and let me know the answer. I'll write again. So it's MVI accumulator which is 3 4H and RLC RLC RLC. So the what is the final components in the accumulator? Okay, so I've got answer A1H. So let's try it quickly. So Z 3 is what? 0 0 1 1, right? and then we have 4 is 0 1 0 0. So this is the first operation. The second will do a left rotation, that means 0 1 1 0 1 0 0 0. The second will do 1 1 0 1 0 0 0 0. And the third one will do 1 0 1 0 0 0 0 0 1. So this will be the final. So this is 1 0 1 0, which is H, and this is 0 0 0 1, which is 1. So the final contents will be A1H. I hope you got the same answer, right? Yeah, A1H is the correct answer. So you can also write A1H, capital H. It's completely fine. But yeah, I think I should not write it in the box. So this is A1H. Okay, I hope this is clear. I mean, these are a lot of instructions that you need to remember. So this is LDAX, there is increment, there is decrement, then there is that jump not zero. So there are a lot of instructions. You just need to go through the lectures. So this topic is actually pretty easy. So I think this is the last question that I have for today. So it says what will happen to the contents of a stack pointer in 8085 after a push instruction is executed. So this is again a direct problem. So every time you have a push instruction, so by push it means, as I said, we have a stack in which we has x1, x2, and so on. So it is nothing but last in first out, right? So every time you push a instruction, your content of the stack pointer is always decremented by 2. So you'll see it in the lectures also. This is a direct problem. So yeah, the decrement will get happen, and it will happen in a step of 2, because this is 2 is for 0, let's say 1 2 something like that. So that is why the contents of the stack pointer moves or always happen in a decrement of 2. So yeah, I mean, just to summarize these processor problems, as you have already seen, we have a lot of instructions. So I'd like you to go through these instructions and at least know the basic working of these. So these problems, like maybe uh, yeah, problem like these could occur in your exams also, that they have given some part of a code and you need to get the outputs, or you need to calculate the number of T cycles, etc. So yeah, I'd recommend please go through this instruction properly, and at least we have it is good that we have one more week to go through some of the more important topics in the microprocessor. So I think we'll be doing some RST and interrupt problem in the next week. That is, I think, given in your assignments for week 12. So yeah, as I'd say again, as I've told already, so the next week, which is week 12, I'll take this lecture on the coming Tuesday, which is 7th October. And week 13, I'll take one more summary session, which I'll take on the next Friday, which is 10th October. So this will be a summary session, and this will only be a 1 hour session in which I'll try to uh, give you some of the important topics and important problems that I think or that I feel are very important. But yeah, this is completely as per my opinion, so I can only tell according to me what is more important, or what is so maybe we'll go week by week and see what are the more important topics in all these weeks. So yeah, this is all from my side for today. If you have any query, you can ask quickly. Otherwise, we can wrap up the session. Let me stop the recording.